All right, so now for this section 2.5, we're going to take a look at these what are called transformations of functions. Transformation basically means you do something to the shape of a graph and it looks like a new graph. And what we're mainly going to be considering, or I guess comparing things to, are the parent functions that we know and love from the previous section. The first type of transformation we'll look at are what are called shifts. And there are two types of shifts. There's going to be a vertical shift, up or down, or a horizontal shift from left to right. So for vertical shifts, here's how they behave algebraically. So g of x plus k will move g of x up by k units. G of x minus k will move the graph of g down by k units. So the whole function gets shifted either up or down by that amount. So we'll take a look at that for these particular examples here. So let's first consider this is x squared plus 4. So here our g of x is x squared. So consider the parent function x squared. So this is just g of x equals x squared. That's not the function we want to graph though. We want to graph x squared plus 4. So what we're going to do is we're going to grab this function and we're going to shift it up 4 units. So I'm going to go up 1, 2, 3, 4. And in red, let me just draw our shifted up version of this. So this is x squared plus 4. So that right there I think gives you a really good idea as far as what the transformation is doing. It's just grabbing the parent function and then shifting up by 4 units. Okay. Similarly here, this is radical x minus 1, or negative 1 plus radical x. The square root of x we saw. So the square root of x was this parent function, radical x, if you recall from the previous section. Radical x plus negative 1, it's really minus 1. So we're adding a negative number to that function, so it's going to shift it down by 1 unit. So I'm going to go down 1 unit vertically. And in red now, I'm going to graph this function f of x, which is a negative 1 plus radical x. Or if you like, radical x minus 1. But yeah, that's all it is there. So as far as vertical functions go, or vertical shifts go anyways, it's fairly obvious. If you add something to a function, you're shifting the graph up by that amount. If you're subtracting, you're shifting it down by that amount. Horizontal, people get kind of confused, so let's see if we can alleviate that. So horizontal, it's quite the opposite. So first off, instead of adding or subtracting outside to the function, we're adding or subtracting inside. In other words, we're adding it or subtracting it to x itself. Okay? Now, if you subtract, you're actually moving it in the positive direction to the right. If you're adding a number, then you're actually moving it to the left. We can try to see that by reasoning it out, but generally what people remember is that what happens on the inside is opposite of what it appears. Subtracting we think of in the negative direction, but since it's on the inside, it's actually in the positive direction, because inside, what happens on the inside is opposite of what it appears. What happens on the outside is what it appears. What happens on the inside is the opposite of what it appears. Okay? So now let's look at this. This is a transformation of x squared. If you remove the minus 3 part, you just get the parent function x squared. So we're transforming the same function we transformed from the previous example, x squared. But now we're going to move it over how many units? We're going to move it over 3 units. Do we move it over to the left or to the right? Yes, we move it to the right because it's minus 3 and it's opposite of what it appears when it's on the inside. So I'm going to move over 3 units to the right and just shift over the whole function. So this is x minus 3 all squared. Okay? And similarly for this one, let's see, x cubed, if you remember. So if you remove the plus 2 part, it's just the parent function x cubed. So x cubed will look like this. This is x cubed. X cubed, there we go. Well, I mean cube root of x really. So the cube root of 2 plus x of 2 plus x is just the cube root of x transformed. So if we graph cube root of x, that was this from the previous section. And what are we going to do? Well, we're adding 2 on the inside, so we're going to shift it over to the left by 2 units. So we shift this over to the left by 2 units. We arrive here at -2, and the whole graph is just shifted over. So this is cube root of 2 plus x. Now let me try to give you an idea here. On the inside, what you want to do is you want to set it equal to 0. If you were to set this equal to 0, you get x is equal to positive 3. If you set this inside equal to 0, you get x is equal to -2. So this is one way you can actually reason if you move it to the left or to the right. Set the inside equal to 0 and see if your corresponding value is, well, positive or negative. And you can clearly see here that the 0 of this function is positive 3. Not -3, positive 3. So notice the red graph here, the only x-intercept we have, which is at the 0, is at positive 3. Similarly here, this supposed graph of the function has a 0 at -2, and that's indeed a 0 of this function, -2. Okay, next we're going to take a look at another type of transformation before we bring everything together. And what we're going to take a look at are reflections. We'll see that right now. Okay, so now for reflections, I say the following. Negative g of x reflects about the x-axis, where g of negative x reflects about the y-axis. Okay, yeah, so there is a horizontal reflection about the y-axis and a vertical reflection about the x-axis. So kind of what we saw earlier, things that happen on the outside of the function affect things vertically. About the x-axis is a vertical flip, whereas things that happen in the inside affect horizontal. So a y-axis reflection is a horizontal reflection, horizontal flip. Okay, so reflections are often thought of as flips, flipping about the x-axis or y-axis. So let's see that here. Radical x squared again looks like this. But now in red, let me graph radical negative x. So radical negative x is what kind of a reflection? It's affecting x on the inside, so it is a y-axis reflection. So it'll look like this. It's a horizontal flip. So this is radical negative x. Okay, very good. So now moving on, f of x equals negative x cubed. X cubed, if you remember, looks like this. Okay, very good. Negative x cubed is grabbing this whole thing and flipping it across to the x-axis. So that'll look like this. So this is the graph of negative x cubed. Okay. Now what we're going to try to do is we're going to attempt to bring it all together by applying all of the transformations that we've seen. Let me just say there is one more bit of transformation that you may come across. We're not going to focus on it too much. So if you do see it out there in the wild in homework problems, let me just say that you don't have to show it when you graph. Maybe I'll do an example of that after these, but let me just explain what they are. So if you multiply by a number on the outside, it will stretch the function vertically. If you multiply by a number on the inside, it'll not stretch the number horizontally, but it'll do the opposite. It'll actually shrink the number horizontally, shrink the graph horizontally. So there are these what are called stretches, basically. So we're either stretching vertically or stretching or shrinking horizontally. These are what are called non-rigid transformations, so I'm not going to talk about those. I'm only talking about the rigid ones. Why it's called rigid is because it doesn't affect the shape of it. I mean, well, the shape isn't really affected, but just think of stretching and shrinking as a non-rigid motion where you'd have to kind of melt things, so to speak. When I think of rigid, what comes to my mind is like a metal object, like something that is solid, and in that case, to bend it, you would have to mess with it, basically. You'd have to mess with the structure of that object, and that's what I don't want to do here. So though shrinking and stretching may be present in homework problems, you don't need to show it too much when graphed. Just mainly focus on the rigid transformations. But again, I think I'll do an example after this. But getting back to this. So this is 2 minus x minus 3 all squared. So if you remove the minuses or pluses or numbers, we're just left with x squared. So let me write this. I'm going to write the following. And this is something I encourage everyone to do. So p of x is just that function I'm describing without any of the other decorations. It's just x squared. Why am I using p? Because p for parent. So the parent function here is x squared. So let me graph the parent function x squared. And now we're going to apply some of these rigid transformations to x squared. So this is p. So what do? Well, x minus 3 is on the inside, so we're going to shift it over to the right by 3 units. Okay, good. That's one thing. So let me write that here, to the right by 3. What else? Well, we are also going up 2 units because we're adding 2. But now there's a negative on the outside of these parentheses. And when you multiply by a negative on the outside, what is that? That is a vertical reflection. That's a reflection about the x-axis. So it's, let me just write this. Let's say it's a vertical flip. Because of this negative on the outside. Now there are a few ways of doing that, but first let's apply the shifts first. So if we apply the shifts first, we're going to the right 3 and then up 2. We arrive at this point. And now the question is, do we reflect over to the x-axis completely, or do we just flip in its own right? So the question is, will the parabola look like this? Well, will it look like this after flipping, or will it reflect across the x-axis completely and look like this? And there's a really nice way of telling. We can just plug in 3 and see what we get. Now when you plug in 3 into the function, you get 3 minus 3 is 0, 0 squared is 0, and 2 minus 0 is 2. So it's not negative 2 we're going to get positive 2. There is still a flip though, but that's not across the whole x-axis, it's only at this point itself. So let me draw that in red actually. So the graph we get is the following. We get this. So this is f. Perfect. And we're going to do something very similar for this one. This one's a little more complicated, to be quite honest. It's 2 minus radical 3 minus x. So the parent function is what here? I should box all of these things because these only help us graph. So our parent function p of x is, what do you think? I hear you scream out radical x. You should be. Because if you remove all signs, positive or negative, and all numbers, you're only left with the square root of x. The main big operation we're doing, basically. Okay, good. Now, aside from that, what are we doing? Well, you have to be a little careful. But you're adding 2 on the outside, so that's going up 2. Now on the inside, are we subtracting or are we adding 3? Well, on the inside, we're actually adding 3. But again, you have to be a little careful because there's a negative in front of x. And the negative in front of x means we're multiplying the inside by a negative. So one way to think of this possibly is maybe the inside is negative x minus 3. So really, instead of adding 3 on the inside, we're subtracting 3 from the inside. Now I know that's a little detailed and kind of technical, and to be honest, we don't really need to worry about that. You'll just kind of pick one. I know that sounds weird because you may think, well, moving to the right 3, moving to the left 3 is different. They're not the same. I'm not saying they're the same. I'm just saying, do we think it's addition or do we think it's subtraction, and then claim what we think we need to do and then figure out from there. So in this case, I'll just say adding 3 on the inside because it's positive 3. I'm going to say that's adding 3, and when you add 3, you move to the left 3. Okay, so just bear with me. There is a negative in front of x, and when there is a negative in front of x on the inside, that is a reflection about the y-axis, so that's a horizontal flip. Horizontal flip. And there is also a negative on the outside of the parent function. There's a negative on the outside of the radical. Negative on the outside is a reflection about the x-axis. So that's a vertical flip. Okay, great. So now what? Well, we need to put all this together somehow. First, let's start off with the parent function. So the parent function is the square root of x. It's just this. So let me label that as p. And now I'm going to apply all of these. Let's apply the shifts first. So I'm going to go up 2 and over 3. So if I go up 2 and then over to the left 3, I arrive here. Now, as far as the image goes, the image is going to be reflected vertically and horizontally. So if you flip this vertically, you get this right here. If you flip that horizontally, you get this. So this is the shape we're going to get in the end after doing our flips. Now, it is actually not going to be over here, I don't think. And the reason isn't very obvious. I guess we'll have to see. Well, remember, this is negative 3. So the question is, if it was actually like this shape, plugging in negative 3 should give us positive 2. Okay? But when you plug in negative 3, you get 3 plus 3 because of the double negative. So you actually get 2 minus radical 6, which is not positive 2. It's a little bigger than 2. Well, I guess a little less than 2, really. So how do we get positive 2? We get positive 2 when we're subtracting 0. So 2 minus 0 is 2. And 0 occurs when x is equal to positive 3. So remember what I said, set the inside equal to 0. That will only help. So when you set the inside equal to 0, what we really get is x is equal to positive 3. So really this moving to the left 3 is actually moving to the right 3. Why is that the case? It is because of the horizontal flipping. I know it sounds funny, but the best thing to do is to plot things in after the fact and use that in conjunction with your transformation. Now, I'll admit, this is a pretty complicated problem, so we probably won't be seeing too much of this, but the ideas that I'm exploring here, you'll definitely see throughout. Okay, good. So when x is equal to positive 3, so let me see if I can, that's fine. There's some overlap of the graphs, but that's okay. So when x is equal to positive 3, we get y is equal to 2. So this is the point we're actually going to be on. So this is a point on the function. And the shape is like what I'm drawing here. So this should actually be not over where it was over there, but over here actually. So that's really what the graph looks like. It's that red. And just to show you, let me erase the parent function p. And just because I can't really tell if it's coming out good in the screen or not, I'm going to go over it in black. There we go. And there is actually an X-Intercept. Where is the X-Intercept? Well, think of it like this. 2 minus 2 is 0. So when this square root is 2, when the radical is 2, then that would make the whole thing 0. When is the radical 2 though? The radical is 2 when you have a 4 inside. So the square root of 4 is 2. So that would need to be 3 plus 1. So at x equals negative 1 actually, so we're spot on as it turns out. The graph looks exactly as it should if you were to graph this in your graphing calculator. By the way, all of these you can do on your graphing calculator. You would press graph on the top left in the TI-83, and then you would go to y equals, and in this case you would go to y equals 1. So the graph button, by the way, looks like this, like a blue bar. You press y equals first though. So the upper left on the TI-83, you press y equals. Okay? And then for this one in particular, you type in y1 equals 2 minus the square root of 3 minus x, close parentheses, then you would hit graph, and you should see an image like this. All right. Now another spot for error is typing in negatives instead of minus. So the minus symbol is in blue and the negative symbol is in parentheses. So the negative symbol is when you want a number to be negative, not when you're subtracting. So keep that in mind, or else you'll get something entirely different. So I said I would do a problem that involves those non-rigid transformations, just to kind of show you what it is and how we handle that. And we'll see an example of that right now. Okay, so I took a quick look at the homework problems, and to the extent that this appears as basically just a 2 on the outside. Right. So we don't really need to see multiplication on the inside, but I did mention what that does. We didn't see an example of it, but that's okay. You won't be tested or anything like that. But in any event, let's see. So the parent function here is going to be just square root of x. And it looks like this. Now 2 radical x is going to look exactly like this. The only difference, though, is that it's going to be stretched vertically by a factor of 2. So imagine grabbing this same function but stretching it up by a factor of 2. And it would look something like that. So that's all we're going to do. That's all you're going to do as far as that goes. So if you're graphing something that involves a number on the outside, just try to show it by stretching it vertically, but you don't have to worry about the specifics of it. If you wanted to worry about the specifics, let me kind of just share them with you. So this is radical x and this is 2 radical x. So when you square root 1, you get 1. When you square root 4, you get 2. Good. Now, if we're stretching this, well, when you plug 1 into 2 radical x, you should get 2. So it doesn't look like it lines up correctly, but imagine it does. So this is 2. Similarly, when you plug in 4, you get, well, double that point. So you get 4. Which should make sense because this height is stretched up by a factor of 2. So we're just stretching things vertically by a factor of that number. Same thing here. This is 2, but it's negative 2. So not only are we stretching, but we're also flipping, because negative on the outside is a vertical flip. So here, p of x is x squared. So just to remind us, let me graph that here. That's x squared. And we're doing 2 things. Well, I guess 3 things. We're stretching it vertically by a factor of 2. We're flipping it across the x-axis. We're also shifting it up by 1 unit. So shift up by 1 unit, up by 1. There is a horizontal flip. And there's a stretch of 2. Stretch vertical by 2. So that's what we're going to be applying, the transformations we're applying to that parent function. So shifting it up 1 unit, flipping it horizontally will give us this. And the vertical stretch by 2 is really hard to show. Basically, you just make it skinnier. If you imagine grabbing this parabola and stretching it by 2, by a factor of 2, it gets skinnier. So let me show that here. In fact, I should have done it in red, shouldn't have I? So let me do that here in red. There we go. So again, I'm not being specific, I'm just kind of saying more or less what it is. Really what I care mostly about are the rigid transformations. The non-rigid transformations, such as stretching or shrinking, you can kind of show, but you don't have to be super accurate about it. But in any event, that's it for 2.5. I really hope we enjoyed 2.5. We saw a lot from 2.4 there, so even though 2.4 was kind of a relatively small section, we see a lot of the ideas of parent functions explored here. So I really hope this helped, and I'll see you in the next video for 2.6. See you then.